Here's what we did today, and it was a rain-shortened class. We had a good 35-40 minutes, but we skipped the last 10 minutes of class or so because it started to rain instead of moving indoors because it takes me so long to pack everything up. So here's what we did. We did problem 17 where they asked for the unit tangent, the unit normal, and the curvature, but they didn't give us specific t value. So we have to do all this stuff in terms of t. But luckily they gave us a helix, which has really nice properties. So here's our prime. Here's the size of r prime. And you got to simplify this. This 9 sine squared plus 9 cosine squared adds up to just, this is 9. So 1 plus 9 is 10. Square root of 10, that's actually pretty good because there's no t in it. So if I have to do anything with the size of r prime, it's not a scalar function of t, it's just a constant. So here's big T. Big T by the recipe is r prime, the vector, divided by the length of r prime. No worries there. You don't have to do anything to it. I would write the little 1 over square root of 10 out front, but you don't have to. It's fine. But it kind of writing out front reminds you it's just a constant. So now t prime, I got to take t prime, and I don't have to do the derivative of the scalar function times the vector plus the derivative of the vector function times the scalar, because this is just the scalar function is literally just a number. So keep the number and take the derivative of this vector. So there's t prime. That's it. Then the length of t prime, again, you get the nice result. 3 over square root of 10. That's nice. So big N, unit normal, is t prime over the length of t prime. So there that is. The square root of t's, or sorry, square root of 10's die. The 3's should cancel. I didn't cancel the 3's. I should have. This is a really nice vector. Just 0, negative cosine t, negative sine t. That's great. And that's big N. But what you do is, let's say you're doing this for a grade, and this is going to be on the practice test. Or sorry, it's going to be on the actual test. N is supposed to be a unit vector, so we real quick check, and this is, I didn't cancel the 3's. I should have. But in any case, these guys are supposed to be squared. And I have the square root of 9 over 3, which is 1. So it is a unit vector. Good. And it's supposed to dot to 0 with t. N and t and b, if we calculate b, supposed to be mutually perpendicular. So you can do the math here. Here's the dot product of n and t. I think I have t first. So it's t dot n, but dot product is commutative. So this is okay. And it does, everything cancels out. So they dot to 0. That's really good. So if you're working where you don't have the answers in the back of the book like we did, you can still check. Because imagine, you did your big N, and it turned out to be a unit vector, and it dots to 0 with t. Those are two really good indications that you're doing okay. Because if you screwed something up, it's not going to, your work isn't going to satisfy both of those if you made mistakes, And so the last thing was the curvature, which is the size of t prime, that's vector t prime, divided by the size of r prime. And so 3 over square root of 10 divided by square root of 10, that comes out 3/10. And that's the book answer. What I like about it is that's constant curvature. And if you think about a helix being a spring shape, then everywhere along that helix is basically the same place. The structure is the same everywhere. So the curvature doesn't depend on t. The curvature of that curve is the same everywhere. If you were a bug crawling along this circular helix, you wouldn't be able to tell where you are. You wouldn't be able to say, oh, this is the lumpy part. It's the same all the way through. So that was number 17, and then we had time to just barely start the next section, which is partial derivatives. Now, we did partial derivatives in differential equations, so you've seen this idea before. Here's z equals y squared minus x squared, and here's the partial with respect to y, the partial with respect to x. Here's f, function of x and y, partial of f with respect to y, partial of f with respect to x. Let's see if we did that right. So you treat x as the variable. Cosine y is just a fancy constant. So the derivative of 5x is 5. The derivative of x cosine y is cosine y. Plus y sine x, y is like a constant out front. So the derivative is y cosine x. Derivative of f with respect to y. Now y is the variable. So the derivative is going to have a minus sign. X is just the number in front. So that's negative x sine y. And the derivative of this, the derivative of y is 1. So it's 1 sine x. And that's what we did today.